So in this video, I'd like to introduce you to some more advanced VHDL concepts that we're going to use to implement our sequential circuits, including finite state machines. But before we get to those concepts, I'd like to take a minute to review something that we've already talked about, which is using a process in VHDL versus not using a process in VHDL. Recall that if we don't use a process in VHDL, that all of the statements are going to execute simultaneously. They are going to all execute at the exact same time. Everything is going to run in parallel. If we do use a process in VHDL, then the way it works is like this. It's going to run everything sequentially, one line at a time, from top to bottom, just like we're used to in other programming languages, but the values themselves aren't actually going to be changed until the very end of the process, until the process is over, and then at that point, any values that need to change are going to happen simultaneously. They're going to happen at the same time. This is important because remember that when we're writing VHDL, the whole purpose is that we want to simulate a circuit. So our code needs to behave in the way that a circuit does, and a circuit operates in parallel. There are many things happening at the same time. So why this matters for us is because up until this point, you've actually probably been able to get by without writing a single process. We haven't needed processes to do any of the things that we've done up until this point. In fact, if you have a purely combinational circuit, I would recommend not using a process. Even though you could, I would recommend not using a process. From here on out, since we are talking about sequential circuits, we are going to be using a lot more processes. In fact, pretty much all of our VHDL modules are going to contain a process from this point forward. So with that in mind, let's take a look at a few additional VHDL concepts that also interact with processes that can help us define some more complex circuits. The first construct that I'd like to talk to you about is an if-else statement. So here you see right away, right, I have a process. And again, just as a little refresher, the stuff inside of the parentheses is what we call the sensitivity list. And what that means is that if the value of A or the value of B changes, then this process is going to execute, right? This process will run if A or B changes values. So that is what a sensitivity list does for us. And so then inside of the process, we are allowed to use this if, else, and if statement, right? That allows us to specify specific conditions. If you've programmed in a different language, such as Java, this syntax should look pretty familiar to you. Notice that we are required, right? If we change the value of an output in one particular case, we are required to change that value in all cases. So we must define all outputs under all possible input conditions. The safest way of doing that is to ensure that your if statement contains an else block at the very end. That way you know for a fact, right, that every possible input condition is covered, and we will also have a value set for every possible output. So this circuit right here is actually a combinational circuit. It is not a sequential circuit. I'll actually show you an example of a sequential circuit a bit later on, but it does use a process, and it does use an if statement within this process. Now you actually can't use if statements without the process. An if statement can only be used inside of a process declaration. Okay, so that's the first concept. The next concept, the next new VHDL feature that I'd like to show you is a case when statement. Now we've actually already seen when else statements, which have been very useful to us in the first couple of labs, right? This is a little bit different. Again, you'll notice that I'm inside of a process here. This takes place inside of a particular process, right? And so the way that it works is we specify what we want to use to inspect, what we want to use to make our decision. In this case, we're using the signal called E, which you notice is in our sensitivity list, right? And then we have a series of when statements. So when E is equal to 0, 0, then I want to set A equal to C, and I want to set B equal to D. And then I have a case where E is equal to 0, 1, then I want to set A to D, and I want B to be set to C, right? And so on and so forth. When others is actually very similar to an else statement in this regard. It's actually required. So you need an other statement when you have a case statement. It is 100% required. So the traditional thing to do is to use it to replace the last combination of your input value, whatever that happens to be, right? Now, you may be asking at this point, what's the real difference between case and an if-then statement? And actually, there is not a whole lot of difference between using an if-then-else statement versus using a case-when statement. They serve very similar purposes within your VHDL modules. You should pay attention, however, to what the resulting circuits look like when using an if, then else versus using a case-when statement. So you can see that a case-when statement most closely corresponds to the use of a decoder, right? We have a decoder set up such that when we examine the value of E in this particular case, right, one of these outputs from the decoder will be active. And so I can combine that with some additional values, with some additional gates rather, over here, some additional AND gates, to set the value of my outputs A and B. So a case-when statement corresponds very much to a decoder. An if-then-else statement probably is more equivalent to a multiplexer for most purposes. And so which one you choose, right, you might be able to code it up the same way using an if or a case statement. You might be able to get it to work using either particular construct, but it may be a little bit simpler to use a decoder in some cases. It may be simpler to use a multiplexer in other cases. So it's nice to have the option. The bottom line is you need to remember that everything you write in VHDL is ultimately going to become a logic circuit. So you need to understand what part of that circuit is represented by which piece of VHDL code that you write. The next construct that I'd like to talk to you about is this idea of variables. So you've probably already seen variables in other programming languages. In fact, we've already seen something that's kind of similar to variables in VHDL, that is signal definitions. But you can also actually have variables within VHDL as well. Here's an example of how variables might be used. Now this definition here, this first line, a set to 3A in hexadecimal. That's what this is saying. The X here represents a hexadecimal value, and then we see the hexadecimal value in quotes afterwards. This is a traditional signal. A signal can be thought of as a wire within your circuit in the strictest sense. This next line here is a variable assignment, and you can tell it's a variable assignment because it's using colon equals instead of the angle bracket equals notation to set the value. So y is in fact a variable. Y is a variable in this particular case. And then you see that on the following line, I take a signal called b and I set that to be the value of y. And then down here on the following line, right, I redefine y in terms of itself, and then I use y to define yet another signal. Now, how does this differ, right? How does using a variable differ from the signals that we've already seen and we've already been using in our VHDL modules? Well, variables don't actually correspond to wires. Variables are more like abbreviations. I think it's easier to think of variables as allowing you to abbreviate the values for some particular assignments. And so when it comes to evaluating this section of code, we're actually going to just substitute the value in, right, whenever we see y. So if you look at the equivalent code down here with the variables removed, you see the first line remains unchanged. The second line just simply takes the value of y and substitutes it in for the value of y. And then the third value down here, right, again, takes that updated value of y and substitutes it in for the value of y on the right-hand side of the signal assignment. So variables are not strictly required. The reason that we use them is to make our code a bit more understandable. We can use variables to represent important pieces of our code, right? And that way it makes our code easier to read, easier to understand. But again, just to reiterate, a variable does not explicitly correspond to a wire within a circuit. In fact, a variable does not really correspond to anything within your circuit. It is simply a way of creating shorthand abbreviations that can be substituted into other expressions. The signals themselves represent wires that exist in your logic circuit. Okay, so now that we've covered a few concepts, let's talk about how we can synchronize things within VHDL. If you have watched the previous videos and worked on the previous sections, you know that in order to synchronize things within our circuits, we need a clock, right? And that clock is usually going to be used as part of a flip-flop. So we have a clock that is going to control a flip-flop, which is going to store information for us. It may be a state, it may be something else, it doesn't really matter. But how do we actually code that up? Well, here's an example that uses a clock within a process to synchronize some signals within a digital circuit. The first thing that you should notice is the sensitivity list, right, contains the clock, and only the clock. So there are no other values contained within this sensitivity list. That means this process is only going to operate whenever the clock signal changes, right? I'm only going to change my circuit values when the clock signal changes. That means they're all going to happen at the same time. They're all going to be synchronized based on the clock. Now, that's nice, but that's not the whole picture. We've specifically been using the rising edge of the clock. So we've specifically been synchronizing our circuits when the clock signal goes from low to high. So to make that happen, you see that I've got an if statement inside of this process that specifies if the clock is going from low to high, if it's the rising edge of the clock, then I want to go ahead and implement my logic circuit. So everything that we see after if rising edge clock in this particular slide is just the implementation of our circuit in VHDL code, right? So this particularly simple circuit, right, it looks like we have an enable bit. If enable is set to 0, then our output will be nothing. If the enable bit is not 0, that means it's true, that means this component is enabled, then we'll do a simple XOR statement. But the way that we have this process set up, the way that we are checking for the rising edge, right, this will only ever execute on the rising edge of the clock. And this S value that we see assigned here, this signal assignment statement, indicates that we have a flip-flop for this particular signal. So anytime I have a signal assignment taking place within a process that's based on the clock, specifically based on the rising edge of the clock, then I'm going to have a flip-flop for that particular signal in this circuit. So this circuit, if I were to draw it up as a circuit diagram, you can see would be fairly simple. I would have a flip-flop, right, with an enable bit called S, and I would have an XOR gate being fed in to that, and then the output of that would also actually be fed into the exclusive OR gate, right? You should be able to sketch this out on a sheet of paper. In fact, I might ask you to do that in a future class. Hint, hint. Notice also on this page, right, we can have asynchronous stuff. We can have combinational logic in the same module. Not everything has to be within a process. So consider what that means. That means that this process is going to run line by line. But remember, the process signal assignments don't take effect until the very end of the process. And those assignments are going to happen at the exact same time as this particular assignment here. So whatever the value of S is, it's going to be immediately passed at the same time to Y, which is the output of this particular entity. Just to drive that point home, we can take a look at some examples of different processes that contain synchronous and asynchronous logic. So on this particular slide, you see on the left-hand side, my sensitivity list contains the clock, but it also contains some other values, T and X, right? And so here is my if rising edge clock statement that says, you know, this is going to be synchronizing my logic circuit. I'm going to have at least 2 flip-flops, it looks like, one for T and one for S, right? I have signal assignments to T and S within this rising clock edge part of the cycle, so I'm going to need at least 2 flip-flops. But then down here, after that, I have a simple assignment, right, based on T and X, setting it to Y. This is not based on the rising edge of the clock. In fact, this is not based on the clock at all. So this is asynchronous. Anytime T changes or anytime X changes, the value of y is going to change immediately. I don't have to wait for the clock cycle. The only time I have to wait for the clock cycle is for this stuff that's inside of the if statement. So you can see in this particular case, I have a process that includes both synchronous and asynchronous logic, all within the same place. On the right-hand side, we actually see the same exact code, but this time I've split it up. And now it's in two processes. I've got one process that's entirely synchronous. I know it's entirely synchronous because the process depends only on the clock. The sensitivity list only contains the clock. And you can see the logic then for the synchronous portion of our circuit. And then down here at the bottom, I have a second process that depends on the asynchronous pieces, the combinational pieces of my logic circuit. This is going to be an entirely asynchronous process. In fact, this is the appropriate way of coding up your logic circuits that have both synchronous and asynchronous logic. One process for the synchronous piece, and then another process for the asynchronous piece. Just to be clear, this piece on the left that contains both within the same process is perfectly valid VHDL. It would work. You wouldn't run into any problems if you tried to execute this. It'd work no problem. But from an ease of understanding point of view, from an organizational standpoint, from a design standpoint, it's actually better to keep our synchronous logic and our asynchronous logic in separate processes. And you can use as many processes within a module as you need. You're not limited to one process or two processes. You can use as many processes as you need to accomplish your logic circuit implementation. So break it into pieces. Break it into modular, easy to understand pieces, and keep your synchronous and your asynchronous logic separate from one another. Okay, so we've already covered a lot, but I would like to cover one more concept before I wrap this video up. And so the last thing that I want to talk to you about is something that's going to relate directly to our finite state machine implementations. If you remember from a class that we had last week, I believe, we talked about how states can be enumerated. In fact, they have to be enumerated in order to be represented within our logic circuit. We talked about two different ways of creating those enumerations. There was the binary enumerations, and then there was the one-hot enumeration that could take place. Well, how do we represent that in VHDL? We could hard-code it in. We could hard-code in what all of our states are supposed to be and all of the logic that's associated with it. That actually becomes pretty tedious and can get complicated, especially for larger finite state machines. So in order to make things a little bit easier for us, we have what are called enumerated types. And so you can see up here at the top, this type declaration. I'm declaring a type called color, and I then label the different values that I want to be acceptable for this particular color type. So my color can take on any one of these 5 values that I have specified here. You can see that I also have the ability to set subtypes. So in this particular case, I'm creating a subtype that is a type of color, but can only take on the values from red to blue. That means red, green, or blue are the only acceptable values for this subtype. Now, I don't know how much we'll be using subtypes. They might pop up every once in a while, but I really want you to understand what happens when you declare a type like this. When you declare a type, it's going to enumerate this for you. It's going to decide on binary values for you and substitute those binary values in whenever you define your circuit. So green might be assigned the binary value 0, 1, for example, and black might be assigned the binary value 1, 1, 1, for example. Xilinx will choose those values for you automatically. It will automatically assign those enumerations for you so that you don't have to do that manually. And then what that allows you to do is use these values, these non-enumerated values, within your code. So it makes it much easier for us to understand, and it handles that enumeration piece in the background without us having to worry about it. So you can create signals of these types. You see here I have some signal definitions of this created type that I made, right? And we can set those to any acceptable value. Right? So C1 can be set to red, green, blue, black, or whites. Notice if I try to set it to a value like yellow, for example, I did not specify that as an acceptable value when I defined the type, so I cannot specify that here either. I have to select from one of these named values that I specified when I declared the type. Right? But then you can use this just as you would any other signal. So here you see I've got an if statement that checks to see if C2 is not equal to green, then set C3 to a particular value. If you're using subtypes, then you are strictly restricted to this range from red to blue. So we cannot make assignments that might break that potential restriction. So let's see, P right here, right, which is connected to, which is a signal of subtype primary, can only be red, green, or blue. We can never allow P to be set to any other value that is not red, green, or blue. This is going to come in particular handy when we talk about how to write VHDL modules for finite state machines, which is actually the topic for our next video.